We now consider example 1c, which consists of a beam subjected to a uniform distributed load of 2 kilonewtons per meter, as well as an 80 kilonewton meter couple applied at C. The beam is pin supported at A and roller supported at B, and we said previously that because of the sudden appearance of the reaction force at B, we would need two sets of free body diagrams, one for x less than 16 meters and a second for x greater than 16 meters. Before we get to either of these free body diagrams, however, we first have to solve for our reactions at A and B. We have pin support at A, so we have forces AX and AY. We have a roller support at B. And now we can replace our distributed load with its resultant at its effective center. 2 kilonewtons per meter over 20 meters will give us a 40 kilonewton force, and because it's a uniformly distributed load, its center will be halfway in between, so it will be 10 meters from the left edge. We also have our discrete couple out here of magnitude 80 kilonewton meter. Our equilibrium equations will tell us that AX is equal to 0, that the sum of AY and B is 40 kilonewtons, and finally that if we take moments about A and set that equal to 0, we have a positive contribution from B through a distance of 16 meters, a negative contribution from the resultant 40 kilonewton force through a distance of 10 meters, and we have the couple, which has the same effect everywhere, so minus 80 kilonewton meters is 0. And if we solve for this, we end up with, on the right-hand side, 400 plus 80, or 480 kilonewton meters divided by 16 meters gives us B is equal to 30 kilonewtons. So then AY is equal to 10 kilonewtons. Okay, so with this as background, we can now begin to construct our shear force and bending moment expressions by looking at these two free body diagrams. The first for x less than 16 meters. And to begin, I'll just replace AY here with 10 kilonewton. And I'll keep the distributed load intact until after we've made the cut. So we have here W using our sign convention. Here's V and M, and this distance is X. Now that I've made the cut, I can replace my distributed load with its resultant at its effective center. The distributed load is uniform and equal to 2 kilonewtons per meter. over a distance of x meters, its resultant is 2x kilonewtons, and because it's uniform, its center is halfway between the ends, or x over 2 from A. 2 kilonewton per meter times x meters gives us 2x kilonewtons, and its center is x over 2 from A. Vertical force equilibrium gives us 10 kilonewtons minus 2x kilonewtons minus v of x is equal to 0. So v of x is equal to 10 minus 2x kilonewtons. We could choose to take moments where we like, but I'm going to choose to take moments about A. We have the bending moment minus v of x times x minus 2x times moment arm x over 2 equals 0. But we know v of x, so if I move these last two terms over to the right-hand side, I have m of x is v of x, 10 minus 2x kilonewtons, times x plus x squared. And we can see that we'll have a minus 2x squared plus x squared. The net result will give us 10x minus x squared kilonewton meters. So in summary, for x less than 16 meters, we have v of x is 10 minus 2x kilonewtons, and m of x equals 10x minus x squared kilonewton meters. Now for future reference, we might just note here what happens as x approaches 16 meters. V of x becomes 10 minus 2 times 16, or minus 22 kilonewtons. And m becomes 10 times 16, or 160, minus 16 squared equals minus 96 kilonewton meters. What about the second set for x greater than 16 meters? Now our free body diagram includes the reaction at B. Once again, we'll draw the distributed load as it is until after we've made the cut. And then we can replace it with its resultant load at its effective center. And once again, because it's a uniform distributed load, its resultant is 2 kilonewton per meter times x meters, or 2x, and its effective center is halfway between the ends, so x over 2 from A. On this basis, then, vertical force equilibrium tells us 10 plus 30 kilonewtons, or 40 kilonewtons, minus 2x kilonewtons minus v of x is 0. And so v of x is 40 minus 2x kilonewtons. Moment equilibrium about A gives us m of x minus v of x times x plus 30 kilonewtons times 16 meters minus 2x times x over 2 meters is 0. And therefore m of x is v of x times x, but v of x is 40 minus 2x minus 30 times 16, which is minus 480, and then plus x squared kilonewton meters. The net result is minus 480 plus 40x minus x squared kilonewton meters. So for x greater than 16 meters, we have v of x equals 40 minus 2x kilonewtons, and m of x is minus 480 plus 40x minus x squared kilonewton meters. Now a couple of things to note here. Again, if we think about x being equal to 16 meters, so approaching 16 meters from above, v is 40 minus 32, or 8 kilonewtons, and m is minus 480 plus 16 times 40 is plus 640 minus 16 squared is 160 minus 256 is again minus 96 kilonewton meters. In comparing the values as x goes to 16 meters from below and above, what we see is that v jumps from minus 22 to plus 8 kilonewtons. The jump of 30 kilonewtons exactly matches the reaction at B, and we don't have a discontinuity in m. It's minus 96 kilonewton meters whether we approach 16 meters from above or below. Finally, we might note from our expressions for v and m for x greater than 16 meters what happens at x equals 20 meters at the end of the beam. Our expression for v tells us that at x equals 20 meters, V is equal to 0. And this is what we expect, because if we look at that beam, the right end is a free end with no discrete force and a discrete couple applied. Even though the distributed load extends to the end of the beam, it doesn't contribute anything in terms of a discrete load at the end. So one of our checks on accuracy is if our expression tells us that the shear force matches the discrete load at the end of the beam, which in this case it does, then that's an encouraging sign. By the same token, if we take a look at the bending moment at x equals 20 meters, you'll notice that we have minus 480 plus 40 times 20, which is plus 800, minus 20 squared, and that's minus 880 plus 800, or minus 80 kilonewton meters, which exactly matches the discrete couple applied at the end. So again, this is a nice way of checking that what we've done is consistent with the way the beam is loaded at the end. If we move from left to right with our expressions, we should match the discrete loads that are applied at the end of the beam. Now I could try to sketch the shear force and bending moment diagrams that go with these expressions, but it will be easier here for me to just reproduce the plots that are on the subsequent slide of your PowerPoint presentation or in your PDF file, and we'll just make some general comments here in closing. So the first thing is that we have a piecewise linear expression for the shear force distribution. One of the things we might note here is that V goes to 0 at x equals 5 meter. We can see that from our expression V of x is 10 minus 2x kilonewtons. So at x equals 5 meters, V goes to 0. We had mentioned before it drops from 10 to minus 22 kilonewtons over that 16 meters, and then the jump between minus 22 and 8 exactly matches the 30 kilonewton discrete reaction component in the y direction that exists at B. And then again, we drop linearly to 0 as we go from 16 to 20 meters. With respect to the bending moment distribution, we have a piecewise parabolic distribution, which peaks also at x equals 5 meters at 25 kilonewton meters. So at x equals 5 meters, m is 25 kilonewton meters. And we can see that either by taking the derivative of m of x with respect to x, setting that equal to 0, evaluating the value of x at which dm dx goes to 0, and then plugging that back in. Or we could plot it out and see that m reaches a peak value of 25 kilonewton meters at x equals 5 meters. Again, we notice that at 16 meters, even though we have a discontinuity in V, we don't have a discontinuity in M. We do have a rather severe discontinuity in slope here, so we have a even more pronounced kink in this particular plot of M versus X than we had in our previous illustration. One of the things you might note is that there appears to be a relationship between V and M. In our illustrations in problems 1A and 1B, we had no distributed load. We just had a series of discrete loads, and we found that V was piecewise constant and M was piecewise linear. Now we have a uniform distributed load. V is piecewise linear and M is piecewise parabolic. This isn't accidental, but we'll take a look at one more example before we get to those relationships in section 8.3.